Okay, so that is the what we introduced last time, and sorry I didn't closely follow up my lecture notes. So I realized once I write on this, I realized the symbol is different from last time we used. I remember that's an AB whatever. Sorry about this one, but the concept is the same like this. Okay, so basically here for defining the lead controllers. And that means the phase angle of the controllers at the desired, measured from the desired locations, basically that's positive. From here you can say basically the phase angle is the phase angle of the numerator, which is this angle, and minus the phase angle of the denominator, which is this one. So bigger one minus this one, this is positive. And for the lat controllers, basically similar ideas. We're simply looking for the phase angle here, and from this graphics and in this arrangement, the angle of the numerator is this big, and the angle of the denominator is that big. So basically making the negative, so that is defined as the lat controllers. Okay. So last time we have come up with the one example for lead controller, and today we're going to see one lat controllers here. So let me do this one here. So we consider the same systems. So the same system is this. We consider G. This is the open loop systems, and that is 10 as S plus 1. This is the one we used last time. Okay. And now for this one, excuse me, sorry, for Java update. So for some reasons, we select due to some design criteria. We choose the desired route to be, for this example we're going to exercise is minus 0.25 plus minus 0.25. Okay. So due to certain design criteria, then we choose this one. And again, this design criteria can be from, say, density ratio, or and all on the natural frequencies. Okay. So from this one, we decide to have this. And so the first step is this: if this desired route is right away onto, say, for example, this is our simple closed loop system. Okay, so this is our open loop system. And for initial design, we simply put into unitary feedback without anything. Okay, this is the quickest way. Then basically here, the first thing is we want to check is whether this desired one is on the root locus of this. If answer is yes, then we done the job. Okay, so basically here for this one is this for the system without a controllers. So it's this system. The C over R basically is G1 plus G. Okay. So now we can derive this one. So that is S squared plus S plus 10. So the characteristic equations is S squared plus S plus 10 equal to 0. So basically, let me revise this one into the classical form. So that basically is K and 1 as S plus 1 and equal to 0 here for K equal to 10. Okay, so for this closed loop system without controller yet, and this is one we've seen last time. Okay, we can quickly see. So we can quickly draw the root locus for this one. So here, so this is minus 0, and this is minus 1 here. So for this one, the root locus is this. Okay. So this is minus 0.5 here. Okay, the desired one located basically is here. So this is our desired, and the red one corresponding is this unitary feedback control without controllers. So definitely doesn't fit in, right? So in this way, we need to modify this system such that we can tailor the root locus, that root locus can pass this point. Okay. The other way, without drawing the root locus and to check whether this point is on the root loci of this system, you can use our homework techniques, apply the phase angle criterion to see if not in 180 degrees, then that won't work. Okay. So under these situations, so this is a method one. So using this one, so from here we can conclude is this. Therefore, S is, these are not on the root loci of, let me call the system one. So let me call the system one. Okay, the system A of system A. Okay, the system A is the unitary feedback without controllers. And the second way you can try to determine this one is not on the root locus is we simply apply the angle criterion. So I would say here is the method 2. Okay, so this is method 1. From method 1, the method 1 basically is drawing the root loci. Okay, so that is here. And method 2, and let me detail this technique again here, is apply the phase angle criterion. Okay, basically here we're going to do is to repeat our homework steps is here. So this is our our characteristic equations. So the phase angle criterion asking is this. From here we can rewrite. So the phase angle of S plus 1 must be equal to the phase angle. From here you can see this one. Let me rewrite S plus 1 equal to minus 1 over K. Okay, so that is minus 1 over K, and that one is minus 180 degrees plus L times 360. So that is the phase angle criteria for this. Okay, and as long as any point on the root loci this equation must be satisfied. So right now we check whether I start. For example, let me pick 1 and 0.25 plus. Okay. Because that's a complex conjugate, and we can, let me pick 1 here. Whether this one is the root loci, and whether this is on the root loci, basically we check against this one. So we do the calculations, okay? So that means here, basically this angle is equal to 0 minus S minus S plus 1, okay? So right now we're checking to here. So basically here we're doing is, at here we see what happens, what is this angle here. So basically here is minus S start minus 1 start. Okay, so that is the angle of the numerators minus the angle of the denominator, which has 2 portions, right? Okay, so I modify that one. Okay, so now we can do the calculations. So for this one, basically that is minus, and that is minus 0.25 plus J 0.25 and minus. This one is 0.75 plus J 0.25. So doing the detailed calculation, this is minus arctangent, real part divided by imaginary part. This is the arctangent. the imagined part divided by real part, 0.25 and 0.75. Right? Okay, so from here, this angle is minus I made a mistake here, not mistake, I skipped this. Okay, so here is our complex plane. Okay, let me make one example. So say if we have the 3.J4, so its face angle is defined by this one, right? So here we know is we can utilize this triangle. So basically this face angle is this one, so that is face angle theta equal to arctangent, and this portion is imagined part divided by this portion is this one. So here we have this, apply this. And now for this case, the imagined part is 0.25, and let me write it down. Imagined part is 0.25, and real part is minus 0.25. I need to come up with a minus here. Okay, so basically, if you do this graphically, that one basically is easier to see. So that point is here. We simply want to know this angle. So for this point is, so this is 0.25, 0.25. So from here, you can easily see that it is 175, right? Or you can punch your calculator, but be careful. Your calculators, I believe that will give you minus 45. Depends on most of the calculators, this number, if you punch it, will be minus 40. This one will be minus 45. So you need to convert it. Okay, so here this is minus 135 degrees. Okay, so this one is minus, and I do have a calculation. This time is 80 degrees. Okay, so the second approach is here. You can see is how much this one is equal to minus 143 degrees. Right. So because once we check this one, you can see if this point will be on the root loci, then this face angle criteria must be minus 180, but here is not. So that meaning, from this calculation, that meaning this is a start. This one is not on the root loci of this system. Okay. So can anyone agree with this? Sorry, So from using the second approach, we proceed the detailed calculation. Again, this portion is what we have exercised in our homework there, right? So from here, we can, first conclusion is this. This for sure, as start, this point is not on the root loci of this system. The second one, because for this case, we ask to have a controller designed such that the desired root is on the root locus. So in this way, I will redraw it. So in concept here, for example, here we exercise is on the lead or lag controller. So basically, we're going to add one. So let me redraw the controller, the control system here, okay, for you to follow up. So now to exercise our control system, so here beforehand we added up one controller. And this controller basically taking up the lead or lag controller template. So let me say S plus Z and okay, so here that is we decide that the template we're going after. Okay, and we can go for other templates, for example, pneumatic controllers. But again, in this section, we exercise on this. So I choose this one. So we add up a controller, and then again, we're putting to the unitary feedback system. Okay. Of course, you may ask me, can we put this controller into the feedback loop here? Yes. Okay, you can do it, but that will be a little bit different analysis process. But for stick with our exercise, and we put into feed forward loop here. Okay. So now with this one, then we can see by adding these controllers, we ask this one is on the root locus of the new system. So the new system, let me do this one. So C over R equal to GC G1 plus GC G. So that means the characteristic equations equal to 1 plus GC times G equal to 0. And let me implement this one, KC times S plus Z, S plus P times 10, S plus 1 equal to 0. Okay, so this is the controller B. Let me call the system B. That one is the with controller. Okay, so by adding the controllers, we asking this design is on the root loci of the system. So that means if you will proceed the checking again, repeating the phase angle criteria of these equations, then you will come up with this one, the similar result, and you're asking for that one. So from here you can see, right now for this system, original system, we are lacking 27 more degrees to come to meet this criteria. Right? So basically from here, 100 minus 153, if we can get further negative 27, then we will meet this one. So where the additional minus 27 from? That is from adding these portions, right? So basically that portion, minus 27 degrees, is contributed by this one, right? Again, so this one right now, this one will contribute minus 27 degrees. Okay? Again, if you don't believe this one, then basically you simply repeat it. For this one, you simply repeat the calculation of the phase angle criteria to this system, then you'll come up with this one. Okay? So that means the angle of the GC at a start equal to minus 27 degrees. So from here we can quickly make conclusions. Again, the discrepancies of this one from the design, that is contributed by the controllers. So today I try to come up with the different perspective of the explanations from last time we did. Okay, last time we did is we simply directly apply the phase angle criteria to these systems, then we do the whole thing. And today I do the other way. Hopefully you provide you more kind of thinking. So from here, before we proceed the details, so from here, because this is a minus 27 negative, so basically here we know for this design we do need is a lag controllers. Okay, so that is this one. So now for this one we can implement. So what is this? So basically this one we plug into here. So that is the phase angle of the KC S plus Z, S plus P. And so we can do the calculation here. So KC, basically that is nothing, S plus Z minus S plus P. Okay, so this one basically equal to minus 27 degrees. Okay. And this is the most important step, and you have to come up with this one. Otherwise, for the remaining won't be so accurate. Okay. So once we have this one, then we can proceed to do the analysis. So from here, would that be okay? I erase those portions. Those ones won't be important anymore. So now we stick with this one, and so right now for us is this. So right now let me so say this is the desired. So a start and equal to minus 0.25 plus J 0.25 here. So for making this one, then per our design, the strategy is this is Z. Okay. Here we have two parameters, and we have only one equation, so that provides us a lot of the flexibility. So here you can choose Z and determine P, or you can choose P, determine Z, depends on you like. Okay. So let me do a little illustration. I do have certain calculations. So for example, here I would say, let me try the different scenario. So this is 1. So this is minus 2.25, and this is the minus 0.5, and this is minus 1. Okay. This selection is not arbitrary. And let me first illustrate the one which is not good. So say, for example, you want to get this one. So say if you want to have, so P is here. So for the controller design, you want to assign your P here. Okay, so that is your P value. Okay, so that means if you place your pole of the controller here, so this is the controller P. Okay. And from here you can see, and you can draw it because later on you might draw a few more different figures. Okay, just draw it. So from here you can see this is this angle. And this angle from here you can calculate basically this angle equal to arctangent. This is 0.25. And from here is 0.75. And my calculation given this about 18 degrees. Okay, so in this way you have to also choose the Z, and Z should be here. Okay, you have to choose the Z even smaller. So if this is 18 degrees, Z is still positive. So by all means, you wouldn't be able to make the negative 27. For example, if you choose a Z here, Z can be either even smaller than, I would say, arbitrary, say 5 degrees, okay? And P here has been measured, this angle is 18 degrees. So it doesn't matter, even if you place Z to infinity, this will become 0 degrees. Even for these extreme situations, you won't make it for minus 27, right? So that means if you choose your location of the pole for the controller here, you never can make it for minus 27. You know what I'm saying? So the selection is not arbitrary. Okay, so here I'm showing you is one invisible solution. So right now, from here you should have a get a good feeling is to make this minus 27, and we need this angle as larger as possible. At least 27 degrees, right? Okay, so we look at other scenario. So you probably can do is draw another figure. How about I go with this? Okay, so the different scenario, the second scenario is this. You might put, say, P here equal to minus 0.5. Okay, so again, we have this P. So we desire is the S minus Z and minus S minus P from the start equal to minus 27 degrees. Okay. So now for this one, we decide the P is here, so we can measure it. So this angle basically is 45 degrees. So this angle is 45 degrees. Right? Okay, so now once we have a 45 degrees, so that means this one, the S start minus Z will be equal to 45 degrees minus 27, and that is 18 degrees. So now we're going to determine the location of the Z such that the angle is 18. Okay, so let me call this is the Z here. So from here, probably you can use this triangle. So this is this 90 degrees here. You can utilize this triangle. Let me use original this triangle here. Okay, so this is 0.25, and this one is 18 degrees. So that means the tangent of 18 degrees equal to 0.25, and let me say this distance is x. Okay, so from here you can determine x. That x will be equal to 0.52. Okay, so as long as you determine the distance is 0.52, so from here, from this geometry, you should know this is minus 0.77. You good? Okay, so right now I'm really into the details. So once we have these situations, then we determine, so therefore, our GC as equal to KC times S plus 0.77 and S plus 0.5. So now we have this. So let me put the system into here. So this is our GC controller, and that is KC. S plus 0.77, S plus 0.5, and this is our open loop system, and that is 10 times 1. S plus 1, so let me put 10 here. Okay, so our systems is like this. This is C and this is R. Okay, so how to determine KC? The KC basically from here we applied to determine KC. With these characteristic equations. S plus 0.77, S plus 0.5, and 10 as S plus 1 equal to 0. So this is our characteristic equations. And for this one, we apply the magnitude criteria. So that means the KC must be equal to the magnitude of S plus 0.5, S plus 0.77, and 10 as S plus 1. Okay, and that this one being calculated at S star there. Okay. Be good? Okay, so this one you can proceed the calculations, and that one will be equal to 0.0171. Okay, so right now, basically here is the, yeah, we leave it there, okay. So for this system, we can exercise the MATLAB simulations, okay. The system is type 1 system. The type 1 system meaning if our input is unit step input, then guaranteed the steady state error is always 0. I'm saying so, you can verify it, probably give yourself about a few minutes, just do the calculations. Okay, do the calculation of the output to the unit step input. You should know how to do it, okay? So after a few minutes, you can verify. And so this is the type 1 system. So type 1 system, that means we can have the input to be unit ramp. Okay, so right now in the simulations, I'm going to deal with the unit ramp system. Okay, so before doing that, any questions? So Scott, probably we can have the new section.